Welcome to this next video in the playlist on group theory. In this video we're going to prove that the alternating group on the set of n elements is a simple group that n is greater than or equal to 5. Now this video needs to be watched after the video, which is the previous video in the playlist on group theory, entitled A5 is simple, and in that video we proved that the alternating group on the set of 5 elements is a simple group. We're not going to reprove that here, and indeed we're going to start with the starting assumption that that is true and do a proof by induction and prove that A6, A7, A8, etc. are all simple. Okay, so you do need to know the proof that A5 is simple. Okay, we're not going to be able to reprove that in this video. Okay, so the first thing that I want to start off with is talking about the lower alternating groups. So what about, the other ones, A1, A2, A3, A4? Well, A1 and A2 are just trivial, so we won't even discuss those. A3 and A4, are they simple or not? Okay, well let's just have a little think about this. The alternating group on the set of 3 elements, that's going to be the subgroup of the symmetric group on the set of 3 elements that contains all of the even permutations. Now the even permutations on a set of 3 elements are just the identity permutation and the 3 cycles, because the other 3 elements of S3 are just transpositions and they're not even. Okay, they're going to be odd. So A3 is actually the same as the cyclic group on the set of 3 elements, because it just consists of the identity and then the 2 free cycles. Okay, and the cyclic group on a set of 3 elements, that's a cyclic group on a set of elements with a prime number of elements. Okay, and therefore it is simple. So A3 is simple, however A4 is not simple. We study A4 in the video on groups of order 12 in the playlist on group theory. And we show that the alternating group on the set of 4 elements actually has one and only one subgroup of size 4, the subgroup that contains the identity element and then the 3 double transpositions. Okay, and that subgroup of size 4 will therefore be a normal subgroup, because if there's no other subgroup of size 4, then whenever you conjugate that subgroup by any element of the larger group, you must just get the same subgroup back again, because whenever we conjugate a subgroup by an element of the group, you must get another subgroup of the same order as the original subgroup. And if there's only one subgroup of that order, then of course it's going to be normal. So A4 is not simple. Okay, so that's why we cannot conclude that all the alternating groups are actually simple. A4 is the odd one out. A4 is not a simple group. Okay, right, but from A5, A6, A7, all the way up, from A5 upwards, they are simple groups. Okay, so let's begin then with the proof. So how are we going to actually do it? Well, we're going to do a proof by induction. Okay, so we know from the previous video that A5 is simple, and that's going to be our starting point. Okay, what we're going to do is we're then going to make the inductive assumption, and the inductive assumption is going to be that up to a certain point they are all simple as well, and then we want to obviously prove that the next one along is simple. Okay, so we will assume, so I'll just put this, I like to write it out in full when I'm doing a proof by induction. Assume that it's true, and by true I mean that it's simple. Assume true for, let's say, n is greater than or equal to 5, but less than some k. So what I mean is we're going to assume that an is simple for n is greater than or equal to 5, but less than some k. And now what we need to prove, that it's true for n is equal to k, so for the alternating group on the set of k elements. So basically what I'm saying is we assume that it's true for all of the ones up to a certain point. So we assume it's true for A5, A6, all the way up to AK-1, and we're then going to prove that if that's the case, that it's true for AK. And if this is true in general, then it will be true that A6 is simple because A5 is simple, and then if A5 and A6 are simple, then the next one along, A7, will be simple, and then if A5, A6, A7 are simple, then the next one along, A8, will be simple, etc. And then it will just go on and on and on. And so if we prove this, we prove that they are all going to be simple, since we already know that A5 is simple. So that's why you do need to know that A5 is simple before commencing this video, because it's a proof by induction, so we need to know that the starting example is true. Okay, right. So how are we actually going to prove then that the alternating group on the set of k elements is going to be simple? Well, we're actually going to do it by a proof by contradiction. So within the proof by induction, we're going to have a proof by contradiction. So we're now going to assume that AK is not simple and arrive at a contradiction. Okay, so we will therefore assume that there does exist some normal subgroup, which I'll call capital H here. So there exists a normal subgroup, capital H, in AK, such that this normal subgroup is neither the trivial subgroup nor the improper subgroup. So capital H is not equal to the trivial subgroup, which I'll refer to as 1 here, and capital H is not equal to the improper subgroup, which I'm not calling capital G, I'm calling the alternating group on the set of k elements. Okay, so we're going to assume that there is some non-trivial normal subgroup, and we're going to arrive at a contradiction. Okay, so there's the overview of the proof strategy then. Okay, what I want to do now is, before we actually launch into the proof, I want to go over a few prerequisites, okay, a few little pieces of notation and a few little reminders of earlier theory in the playlist on group theory that we are going to use, and which I think it's best to do first rather than having to do it mid-proof. Okay, I think it works better if you've done it up front and then you just use it when you get to the point of the proof, rather than having to, getting partway through a proof and then having to do a huge sort of side bit. Okay, I think this is the better way to do it. Okay, so there are two things that I just want to make sure we're familiar with right from the start. The first is just notational. So remember the alternating group on the set of k elements. All of the elements in here can be interpreted as being permutations, or indeed they really are interpreted as being permutations of the set containing the elements 1, 2, all the way up to k. So they represent permutations, even permutations, of a set containing k elements. Now, of course, you don't have to use these symbols for the set containing k elements. You could use more exotic symbols if you like, but it's customary just to use the natural numbers. Okay, so AK, all of the elements in it, can be interpreted as representing these even permutations of this set of k elements very easily. Indeed, that's how we build it. Okay, now, what I want to do is define certain important subgroups of AK that are going to be important for the proof that we're about to do. Okay, so I'm going to create some notation for them. That's what I want you to get familiar with, the notation and what they are actually meaning. So I'm going to create subgroups which I will call capital G subscript I, and this I here, it can be any number from 1 to k, so 1, 2, all the way up to k, and this is why it is convenient to use the natural numbers here as the elements of the sets here. Okay, and these are just going to be the stabilizers of each of those elements. Okay, so this will be defined to be all the, let's say, sigma, which is an element of AK, such that when sigma acts on little I, it fixes it. So the answer is little I. Okay, so you go through all of the elements of the alternating group on the set of k elements, and they're all even permutations of this set 1, 2, all the way up to k. Okay, and you look for those that fix this element I. So you pick an I. You could have picked I to be equal to 1, and then you'd want all of the permutations which fix 1. If I was equal to 2, you'd want all of the permutations which fix 2, etc. So you've got k of these special subgroups of the alternating group on the set of k elements. And these do form subgroups of the alternating group on the set of k elements, because after all, they are just the stabilizers of certain elements. There's a very natural group action of this group on the set of k elements. These are just the stabilizers of each of these elements. Okay, which is why we're actually using the notation for stabilizers here. Okay, right. Now, so these are subgroups, so I might just write that somewhere. So GI, each one of them is a subgroup of the alternating group on the set of k elements. A proper subgroup, but still I'll just write it as is a subgroup of. Okay, And the other thing that you can conclude is that these structures are actually isomorphic to another group. You can actually say instantly what they're isomorphic to. Now let me explain this. I hope this is intuitively obvious, but still let me explain it. Okay, all of the elements in one of these groups, capital GI, they are even permutations of this set of k elements that fix the ith element. So if I put I in there, they fix I. Is there really any point I being there? Okay, what you could imagine doing is taking the I out and keeping the rest of it, and that would now be your element. And the composition law, you know, all the elements would remain exactly the same. The composition would remain exactly the same because of the fact that all the elements in here, they just all fix I. So it really doesn't have any interesting algebraic facets at all, really. Okay, because whenever you compose any of them together, the thing that you end up with will still fix I. So really, to understand the composition, it's useless the I being there. You might as well think of the elements in this subgroup here as just being even permutations of all of the k-1 elements, which is the set 1, 2, all the way up to k, without I in there. And that's what we can now do. Take away the I, imagine taking away the I, keep all of the rest of the elements of this set, and all of the elements in here can now be interpreted as representing permutations of that set containing k-1 elements, and they're all still going to be all of the even permutations of that set of k-1 elements. Okay, so what I'm trying to say here is that GI will actually be isomorphic to the alternating group on the set of k-1 elements, because really I plays absolutely no interesting role in these permutations. Yes, you can add it on there, but you can also just take it away, and you'll keep this permutation with exactly the same algebraic structure. Okay, so I hope that is intuitively obvious to you. So what we can conclude from this then is that if all of these GIs are isomorphic to the alternating group on the set of k-1 elements, of course by our inductive assumption that means that they are all simple. So these GIs, they are all simple, so they contain only the trivial and improper subgroup as their normal subgroups. There are no other normal subgroups inside of them, and that will be important very soon. Okay, right. So that's firstly a little introduction that I want you to be aware of. The other thing that I want to say up front to remind you of is how you can interpret conjugation in the symmetric group on the set of k elements, and therefore how you can interpret conjugation in the alternating group on the set of k elements, which is after all just a subgroup of the symmetric group on the set of k elements. So long ago in the playlist on group theory I had an entire video dedicated to conjugation in the symmetric group on the set of k elements, and I would advise you to watch that if you're not already familiar with this, but I just want to remind you of it here because it's really important that we understand this. Okay, so there's a very nice interpretation of what conjugation of one element in the symmetric group on the set of k elements by another element actually means. And since, as I say, the alternating group on the set of k elements is just a subgroup of the symmetric group on the set of k elements, you can still understand conjugation in the alternating group on the set of k elements by this approach. Okay, so to illustrate this, let me take an example from S3. I think it's best just to give an example when you're doing something like this. Okay, so I'll take an example. So I'll take but actually let me firstly just write it out more abstractly. So we are trying to conjugate one element of the symmetric group on the set of k elements by another, which we're calling alpha. So we're conjugating sigma by alpha. So let me firstly put in the middle element, sigma, here. Okay, so let's say sigma is this free cycle here, where 1 goes to 2, 2 goes to 3, and 3 goes to 1. So this is going to be our permutation sigma here. Okay, and I now want to understand what it means to conjugate this element by another element. Okay, so we're going to get some other element, but we get an element that's very much so related to this element here. Okay, and let me explain the reason. The way that you can interpret conjugation of an element in the symmetric group on the set of k elements is that you can interpret it as you are leaving the arrows the same. If you've got a picture of the element here, the picture of the permutation, you can interpret it as you're leaving the arrows the same, but you're going to relabel up the elements of the set on which the arrows are actually showing a permutation of. Okay, and let me show you this. So, what I could do is I could decide, actually, I don't want these symbols called this. I want to rename a few. I want 1 renamed 2. So I could rub out 1 and rename it 2, and I could rub out 2 and rename it 1. Okay, so I could have a relabeling map in this way. Okay, and let's say I want to keep 3 the same. I have to keep 3 the same here. Okay, so I've had this relabeling map. I've relabeled up the symbols in this way. And now the question is, once I've relabeled the symbols in this way, what now is my mapping? Okay, well now, look, it's changed. Originally the mapping sigma was 1 goes to 2 goes to 3 in cycle notation here. Now what's the mapping? Well, 1 here is going to 3, okay, 2 is here and is going to 1, and 3 is going to 2. Okay, so now it's actually become the mapping 1, 3, 2. Okay, and this is the interpretation that you can have of what conjugation does by another element, that you are effectively relabeling up the symbols on which your permutation is acting, and then what's the new permutation after you've relabeled up the symbols in this way. That's what it means to conjugate an element by another element, and I'll explain that in more detail in just a moment. Okay, right, of course, it doesn't then really change the algebraic structure, because the algebraic structure isn't about the names of these symbols here. The algebraic structure of an element is determined by the arrows, and we're not changing the arrows, we're just changing the symbols. So that's why conjugation doesn't really change the algebraic structure, although it changes the it changes the element, it does change the permutation, but it doesn't really change the algebraic structure of the element, because the arrows are kept the same. It doesn't change the cycle type, i.e. what length cycles you have in your cycle decomposition of the element. Okay, so why does this, is this what we're doing when we conjugate? Okay, well, here, what we can do is we can say, okay, this relabeling mapping, okay, if we're going to do this, let's try and actually do this. If we're going to do this, we need, we can give this relabeling mapping, it's going to be an element of the symmetric group on the set of n elements, or k elements, okay, or in this case the symmetric group on the set of 3 elements. In this case, our relabeling mapping is what? 1 is being sent to 2, 2 is being sent to 1, and 3 is being sent to 1. In this 3 is being sent to 3, rather. In this case, our relabeling mapping is the transposition of 1 and 2, okay? So we could call this relabeling mapping alpha. So here we've got a relabeling mapping, and here's the relabeling mapping going this way as well. Okay, so the relabeling mapping will also be a set permutation of the set of k elements. So it will be another element in the symmetric group on the set of k elements. Now if we want to then work out what the overall mapping, once we've done the relabeling, once we've erased things out and replaced them with what they are, according to our relabeling mapping alpha is, how would we do it? Well, of course, what we now need to work out is from this set here, and I'll just highlight it up, we want to know from here to here, what is the mapping now? Okay, well, of course, we're going to have to firstly invert alpha, because alpha is the map. Alpha, the way I wanted you to define alpha was it was the map from here to here. Okay, so it would have been the same as the map from the green set to the red set. So we're firstly going to have to invert it if we want to go from the red set to the green set. So we'll firstly do alpha inverse, then we'll do sigma, and then we'll go forwards with the relabeling map. We'll go from the green set to the red set, so we'll do alpha. So I hope you now see why this can be understood in terms of conjugation by this relabeling map. Okay, so alpha, the thing that we're conjugating by, you should interpret that as the relabeling map. Sigma is the thing in the middle that we're trying to change, the element that we're trying to change by relabeling up the elements on which it's actually acting. And here then, this is the answer as to what you finally end up with, the element after you have relabeled up the elements of the set on which it's acting. Okay, right. So in this case, what we've effectively done is conjugated the element 1, 2, 3 by the element alpha, which is this transposition of 1 and 2. Okay, so there is the interpretation of conjugation that I want you to have. That if you conjugate one element by another element, you are effectively relabeling up the domain and codomain according to the element that you're conjugating by. So the element that you're conjugating by, it will be a set permutation of the set 1, 2 all the way down to k, okay, and that is therefore effectively a relabeling map. And what you're doing to your middle element, the element that's being conjugated, sigma here, is you're just saying, okay, what would this be if we performed this relabeling to the domain and codomain, and that's your new element. And it doesn't really change it that much, because as I say, we're not changing the arrows, we're not changing the algebraic structure, we're just changing which symbols are actually being moved to which. Okay, right, so you do maybe end up with a new element, but it's going to have algebraic properties that mirror the original element. Okay, so further, what we can actually now say is that if we want to know what the cycle decomposition of the new element is, so let's say we've got the cycle decomposition of the original element, and we'll use our example here. Here's the cycle decomposition of our original element. You can work out the cycle decomposition of the new element, and the way you can do it is just, well, now the cycle decomposition is going to remain exactly the same, because as I say, the algebraic structure hasn't changed. All we now need to do is we need to say, okay, 1 is now going to be called alpha 1, 2 is now going to be called alpha of 2, 3 is now going to be called alpha of 3. Okay, so actually we don't need to change the cycle decomposition at all, apart from the fact that we need to relabel up the elements as they've been relabeled by alpha. Okay, so the new elements, the conjugate of this, all you have to do is go through the cycle decomposition and replace each of the elements in the cycle decomposition with what alpha relabels them up as. So in this case, alpha is equal to the transposition of 1 and 2, so alpha of 1 would be 2, alpha of 2 would be 1, alpha of 3 would be 3, okay, and of course this is the same thing as this, because this is just this one rotated by a little bit. We've just moved the 2 to the front and then moved 1 and 3 along, but of course this is the exact same free cycle as this one here. Okay, so that's the interpretation that I want you to have for conjugation, and here is how you can actually work out if you've got the cycle decomposition of one element and you're conjugating by another element, you can very easily find the cycle decomposition of the conjugate. To complete this little starting portion, this little prerequisite section if you like, let's consider what would happen if I conjugated one of these stabilizers of an element I by an element alpha. So what would alpha gi alpha inverse be? Well, of course, I would conjugate every single element in gi by alpha. Now, all of the elements in gi, think about what their cycle decomposition would look like. Okay, one of the things it would always contain is a 1 cycle for I would be in a 1 cycle because it's fixed by all of the elements and therefore it would be sent onto itself. Okay, now in the answer to this, okay, in the conjugate of this, what now is going to be fixed? Well, what's the new thing that's going to be in that 1 cycle? So I might just show you an example. So if I had an element in here, I would be in a 1 cycle, and then you'd have loads of other cycles as well. Okay, so you might have some cycles here. Okay, so let's say this is an element of the stabilizer of I in the alternating group on the set of k elements. Okay, if I then conjugated it by alpha, which let's say is now an element of the alternating group on the set of k elements, okay, I would now have to just go through and replace all the elements in here with what alpha sends it onto. Okay, and of course now I'd have alpha I in this 1 cycle here. Okay, so in fact what this is going to become is it's going to become another subgroup that's going to be isomorphic to itself, and it's actually going to become all of the elements which stabilize alpha of I. Okay, so when I conjugate a stabilizer in this way by an element of the alternating group on the set of k elements, I'm actually just going to change it into another stabilizer, and it's now going to stabilize the element that alpha maps I onto. Okay, so all of the other cycle decomposition will change as well, but this is the portion that's important. Every element in here will now go on to a corresponding element that fixes alpha of I rather than I. Okay, and you will therefore end up with all of the elements in the alternating group on the set of k elements that fix alpha of I. Okay, and it has to be that way because you have to end up with a subgroup of the same number of elements. There are only a certain number of elements that fix alpha I. You know that they all must fix alpha I because when I conjugate something here, you are now going to get alpha of I in a one cycle in itself. There's only a certain number of elements. They have to correspond one to one, okay, because conjugation is an injective map. Therefore, it must be the case that you end up with this full stabilizer of alpha I. Okay, so that's the final bit of the prerequisite that I want you to know. That if I conjugate one of these stabilizers by an element, it's going to become another stabilizer. Which element is it going to stabilize? Well, whatever the element I, which was initially stabilized, is mapped onto by this relabeling mapping, okay, alpha here. Okay, so all of that is what I need you to be aware of before we begin this proof. So I'll give you a break here whilst you absorb all of this, and then in the next video we'll actually begin the proof.